Okay, hi everyone, thanks for coming. It's great to see many of you interested. Today I'm going to talk about reinforcement learning, touching on what it is, what it can do, and how it works. And that's a short version of a longer tutorial I gave recently, which you can find on YouTube. Just go to YouTube, type this talk title, and you'll get to the video, which includes more details about algorithms and so on. So a brief personal background, I did my bachelor's and master's in Tel Aviv University, worked at Intel for several years, then did a PhD in AI in the University of Texas at Austin with Professor Peter Stone. And currently I'm at GM, where I've been group manager, co-founded the autonomous driving group, and currently applying reinforcement learning for challenges related to the future of transportation. My past research focused on making autonomous agents learn and act in realistic environments. My PhD dissertation focused on the power trading agent competition, where autonomous agents trade energy for the benefit of a smart electricity grid. Additional projects included applying reinforcement learning for smart thermostats, for robotic soccer, and also autonomous ship navigation. So let's start by asking, what is reinforcement learning, also called RL? So here is Rich Sutton, probably the founding father of RL. And according to Rich, RL is agent-oriented learning. It's learning by interacting with an environment to achieve a goal, where learning is done through trial and error. The only feedback the learner has is some evaluative feedback called reward, which is a numeric value telling it roughly how good the current action is. But it doesn't tell the agent what's the correct decision to make. That's in contrast to supervised learning, where the learner is shown examples of correct decisions. Here, that's not the case. The agent needs to figure out the correct decisions on its own. And in general, RL is considered the kind of machine learning that is most like natural learning that you can find in animals and maybe humans. So when getting into a new domain, it's good to see some examples, and the examples I'm going to show are from the RoboCup domain. RoboCup is the World Cup in robotic soccer. It was established in 1997 and today has thousands of participants in several different leagues. From the bottom right, clockwise, there is a 2D simulation league, 3D simulation, small-sized robots, medium-sized robots, and standard platform. And one of the tasks in RoboCup is called half-field offense, where a team of attackers try to score as many goals as it can against a team of defenders. So what we see here is the red team executing a random behavior, where at any point in time, the player selects randomly between kicking, dribbling, and passing. And as you can see, this behavior is not very effective. So we want to improve it. And one way to go about it would be to try to hand code a better behavior into this team. However, a better alternative is frequently to use reinforcement learning. So here is my colleague and friend, Shivram Kalyanakrishnan, did his PhD at UT Austin as well. And during his PhD, Shivram trained simulated soccer robots. And the way he trained them was by telling them that it is desirable that the ball be in a position that is inside the goal, and then he asks them to go figure out how to make that happen. And while that might not be the best strategy to train a human team, it can be pretty effective when you train a team of reinforcement learners. So Shivram sends his team to train on a cluster, and several hours later, they return with the following behavior. So we can already see that the team is able to, thank you, this is not my team, but I agree it's impressive. So we can already see the team can execute plays that involve complex coordination under defense pressure and scoring under tough conditions. And it's important to know that no one programmed this behavior into these agents. It was learned purely from trial and error in simulation. Okay, let's see another example, this time from the 3D Simulation League. Here we have a physical simulator with gravity and friction and models of humanoid robots. And we start by hand coding a humanoid robot walk, which, as you can see, is fairly stable, but is very, very slow. So again, we send our robots to train on a cluster, and several hours later, they return with the following walk, which is much faster, is still stable, and is able to take a ball all the way into the goal. And this walk is just one skill that was learned by the robots. In fact, they have several other skills that were learned as well. And this skill learning process was the secret sauce behind winning several world championships. So here I have a short highlight video for you from the 2017 competition. We are the orange team. Orange is the color of the university. We are called UT Austin Villa after the English soccer team Aston Villa. So this gig was learned using reinforcement learning. And robot movements were learned using reinforcement learning as well. And pay attention to this play. We also have multi-engine technology. And that was one of the nicest goals scored at that competition. Okay, so what did we just see? In the above examples, we didn't program behavior, but instead we wired a performance measure and let behaviors emerge through reinforcement learning. And in general, reinforcement learning, RL, applies to any problem that involves optimizing sequences of decisions over uncertain outcomes. Scientifically, RL overlaps with several fields, naturally computer science, but also engineering, mathematics, economics, and even psychology and neuroscience. And recently, RL has also started transitioning from academia to industry. In 2017, MIT Tech Review ranked it among 10 breakthrough technologies, and I cite, by experimenting, computers are figuring out how to do things that no programmer could teach them. So what can RL do in these days? I have a collection of successful applications. For example, in the domain of robotics, RL was used to teach robots to walk, autonomous helicopters to flight, and manipulation robots to execute complex manipulation skills that no other algorithm was able to execute. In table games, RL achieved superhuman level in a complex game named Go and in the game of poker. In computer games, RL achieved or surpassed human-level play in tens of Atari games and also in complex real-time strategy games such as Dota and StarCraft. So now that we know we have a feeling about what is RL and what can it do, let's see a little bit on how it works. And for that, I'll get a bit more formal. So RL is about learning to act purposefully. And each research area has a defining research question. What question defines RL? For that context, we think of an agent interacting with an environment where the agent continually senses the environment, executes some thinking or decision-making processes, and then selects an action, executes it in the environment, and repeat. More specifically, the agent senses some representation of the state of its surroundings through its sensors, and also this reward signal, which is just a numeric value telling the agent how good the current state is. And in that context, the defining question of RL is how must an agent in an unknown environment act so as to maximize its long-term sum of rewards. RL problems are frequently defined as Markov decision processes, or MDPs. An MDP has a set of states. Here we see 10 states representing possible states of the environment. And in each state, an agent can take actions. So for example, here, the agent can take a green action and move from state 1 to state 3, or it can take a red action and move to one of several states according to some distribution. And similarly for all other states. In addition, each state has a numeric value assigned to it. This is the reward, telling the agent how good it is to be in this state. And I should note that initially, typically, the agent doesn't know about the reward in advance, and it doesn't know about these transition probabilities in advance. That's the part that is unknown in the environment. So, for example, an agent can start in state 1, take red action, move to state 2, getting a reward of -1, take red action, move to state 6 with a reward of 2, and then take a green action, move to state 7 with a reward of 10. And this is how the life of an agent looks like. It is a possibly long trajectory of being in a state, taking an action, getting a reward, moving to the next state, and repeat. And as I said, the goal of the agent is to maximize the expected long-term sum of rewards. With a minor modification, we add a discount factor called gamma between 0 and 1 that discounts rewards that are further in the future. This encourages the agent to get rewards earlier rather than later. And this also helps the math to converge, which is by itself a very important reason to include it. A core concept in an MDP is a policy. A deterministic policy is a function pi that maps a state S into an action A. So when I say an agent is following a policy, I mean that at time t, when the agent is in state st, it applies the policy function pi to get an action to execute at. On the top right, you can see a very simple policy telling the agent that in state A, it should take action 2, and in state B, it should take action 1. And I should note that the number of deterministic policies is exponential in the number of states. So typically, we have a very large space of possible policies. And in this large space, the RL agent is searching for an optimal policy, or if it's not able to find optimal policy, at least a good one. So going back to our example, let's call this expected sum of rewards Q at the bottom. And we can define a Q function that gets a combination of state action and returns the expected sum of future rewards if we are in this specific state, taking an action and then act optimally. And now we are ready to see perhaps the most famous RL algorithm called Q-learning. Q-learning works by maintaining a table like the following, where the rows represent all possible states, and the columns represent all possible actions, and each cell representing a specific state-action combination holds a current estimate of the Q value for this state action. And these estimates are updated based on the agent's experience by interacting with an environment. That's the part that is being learned. And the update is very simple. A piece of experience looks like a tuple of ST, the current state, AT, the current action, RT plus 1, the reward that the agent gets, and ST plus 1, the next state. And based on this piece of experience, we use a one-line update formula to update the current Q value towards some target value by some fraction amount alpha between 0 and 1. And the amazing thing is that as long as a Q-learning agent acts in an environment, do these one-line updates, as long as it acts greedily based on the estimates, and what I mean by greedily is that whenever it is in a specific state, it goes to the table, look at all the Q values for possible actions, and just execute the action with the highest Q value, and as long as the agent makes sure to explore each action enough times, Q-learning will converge and induce the optimal policy. And this was proved by Watkins and Dayan in 1992. And in fact, this proof opened the entire research area known as reinforcement learning. Okay, so far I talked about small MDPs where we have a small number of states, small number of actions. We can maintain nice tables, enumerate all combinations. The issue with that is that in real life, we typically have huge number of states and huge numbers of actions, and we are just not able to enumerate all combinations. So instead, and we're not able to maintain such tables. So we replace the Q table by function approximators. For example, we could use a deep neural network as a function approximator, and then we have deep reinforcement learning. So let's go through several examples. The first big success of RL was probably the TD Gammon program, playing backgammon. TD Gammon is an RL agent that starts with no knowledge about the game and starts to train in self-play, playing against itself. And after playing millions of games and 6 weeks of training, it became the world top player in backgammon, beating all top humans. Inside TD Gammon, we have an algorithm similar to Q-learning. In fact, it's a continuous version of the Q-learning algorithm, where instead of a Q table, we have this neural network that you can see in the middle of the slide, that the input to the network is the game state, the board state, and the output is the Q value, which in this case is the win probability. And that was a very impressive result back in 1992. In fact, it's still impressive. The main problem with it was that it was not clear how to transfer this success to other domains. So a more recent result or success is the DQN agent. DQN is a deep reinforcement learning agent that was developed in a Google DeepMind, which plays Atari. The agent, represented here as the brain, outputs joystick actions which are being sent into the Atari emulator, which returns a representation of the state as the screen pixels and returns a reward as the score difference. Inside DQN, there is a convnet that gets a screen as an input and outputs Q values for all possible joystick actions. And the remarkable thing about DQN is that this was the first time that a single RL algorithm achieved human-level performance in tens of unrelated tasks, unrelated Atari games. The only thing common between them is the input format, which is the screen, and the output format, the joystick, but the games were very different from each other, and a single learning algorithm was able to master all of them. As I said, this is an example where we have a huge state space, so we replace the Q table with a function approximator, the convnet that you have seen in the previous slide. So the box represents the convnet, and whenever the agent is in some state, it propagates the state through the network, gets 18 Q values for each possible action, and just selects the action with the highest Q value. And the question is, how can we learn such a convnet? How can we learn to predict the Q values well? So the core idea is somewhat similar to Q-learning, but instead of updating the current estimate towards some target value, in fact, both sides of the equation are parameterized by a vector W, and the goal is to minimize an L2 loss between the left-hand side and the right-hand side. So find a W that minimizes this L2 loss. And on the way, we run into some convergence issues because in contrast to supervised learning, where the agent is given fixed labels, here no one is giving labels to the agent, so the agent estimates the labels as well. And as you update the parameters, the label changes. So in fact, you're chasing a moving target. And some of the techniques to make this algorithm converge make this moving target move slower and helps the algorithm to finally converge. Let's see how DQN works in a game called Breakout. So again, the agent starts with no knowledge about the game other than the fact that there are 18 legal actions, and it gets a screen and a score. And initially, indeed, it's not able to hold the ball in a game for too long. But as learning progresses, it learns to hold the ball for longer and longer periods. And then, after 600 iterations, something interesting happens. So what we see here is a strategy called tunneling. That's the best strategy for this game. And the interesting thing is that no one told the agent anything about this strategy. It discovered it on its own through trial and error. Okay. Another big success of RL, recent success, is the AlphaGo program. So for those of you who don't know Go, Go is an ancient game, very popular in East Asia. And one of the properties of Go, you can see on the right, a board with stones. And one of the properties is the huge number of possible board positions. The number of possible board positions is much larger than chess. In fact, it's larger than the number of atoms in the universe. And that makes it very hard for computer programs to solve or play. And it was considered impossible for computers even to evaluate who is winning given a board state. This is how an illustration of how the tree of all possible futures look like in a game of Go. So here, the state is a board state with stones. And then whenever we add stone to the board, we move to a new state. And you can imagine that this tree blows up very quickly. But nevertheless, the AlphaGo program was able to beat top human players, really brilliant players in 2016 competition and in 2017. And you can see, look at the players' reactions and to get a feeling on the capabilities of AlphaGo. So what's inside AlphaGo? AlphaGo, similar to other programs, starts with no knowledge about the game other than the game rules. And it learns through self-play to play Go at a superhuman level. So this sounds a bit similar to the TD-Gammon program. However, the problem is much more complex here, and therefore the algorithm is much more sophisticated. The algorithm is a more general version of Q-learning equipped with a powerful triad of a policy neural network, algorithm called Monte Carlo tree search, and a value neural network. A policy network is just a neural network that gets a board state as an input and outputs probability distribution over possible reasonable actions to take. Monte Carlo tree search is an effective algorithm to search this huge tree of possible futures, to run narrow and deep searches, and it's very good at balancing between selecting actions that are already known to have high Q value with actions that have a potential to have high Q value, but for which it doesn't have enough data yet. So combining Monte Carlo tree search with a policy network, the policy network represents the best policy learned so far. Monte Carlo tree search keeps improving it, it continually improves it, and the policy network helps to focus and reduce the breadth of the searches of the Monte Carlo tree search. And in addition, there is a value neural network, another deep network that learns to predict the win probabilities from every state, and this network is used to reduce the depth of the searches. And together, we get a powerful algorithm called search-based policy iteration, where AlphaGo becomes its own teacher. It learns from playing against itself to master this very complex game. Okay, the last group of methods I would like to briefly touch on are called direct policy optimization methods. And going back to our diagram of an agent interacting with an environment, so far I talked about estimating a Q function and then select an action that maximizes the Q function. But this group of methods avoids the need to estimate any Q function altogether. It bypasses it by replacing the entire agent with a function approximator, for example, neural network. The input to the network on one side is the state, and the output is an action. So the network represents a policy. And the parameters of the network gives us parameters. We have a parameterized policy class, pi parameterized by theta. And we would like to find theta such that the performance of an agent that follows this policy, the network's policy, is maximized. So this defines an optimization problem. It's a fairly complex one because we are looking for parameters that when we take the network, put them on the agent and let it play in an unknown environment, the performance will be maximized. But if we look just at the two edges of this problem, the input is a parameter vector and the output is the performance, we have an optimization problem. And if we look at it as a black box, you might think that, well, we might try to use a gradient ascent, like supervised learning. And this is almost the right answer. We have a problem here that we are not able to backpropagate gradients, and because some of the dynamics, the red ones, are unknown. These are, if you remember from the beginning of the talk, the transition arrows between states. Initially, they are unknown, and we're not able to backpropagate gradients. So solution methods typically estimate gradients from samples, and there are different methods for how to do the trading of different considerations, such as bias variance, how much we can reuse data from other agents, convergence, and so on. This is highly dependent on the specific problem we are dealing with. And one of the recent success of one of these methods is learning dexterity. So this is a work done at OpenAI, and we see a robotic hand manipulating a cube to reach some desired target value that we see on the bottom right. And again, this behavior was not programmed into the hand, it was learned completely from trial and error. And what is even more impressive is that it was learned completely in simulation. So learning in simulation is a very good way to get lots of data. We can send many simulation jobs to the cluster, get lots of data, but it is typically known that whatever is learned in simulation does not transfer to the real world. And the reason is the discrepancy in physics. However, the guys at OpenAI came up with several clever tricks and were able to apply the policy that was learned in simulation as is on the robot and get to the impressive performance that you've just seen. So before I conclude, I would like to give some credits to guys whose slides contributed to this talk, my colleague Shivaram and my advisor Peter Stone, and also professors Rich Sutton, Dave Silver, and Dan Klein. For those of you who are interested, there are useful resources on the web. There is the Sutton and Barker classical book, and also some online courses in Berkeley and in UCL. And also, a longer version of this talk is on YouTube. As I said, you should just look up the title of the talk, put it on YouTube, and you will get to the video. And this video is a longer tutorial that contains more details about the algorithms, if you are interested. So feel free to look it up. Okay, so in this talk, I've focused mainly on robotics and games, but in fact, the applicability of RL is much, much broader. It applies to numerous applications. Only some of them are listed here. Some examples I collected are environmental applications, renewable energy management, smart homes, invasive species management, and wildfire suppression, and also financial applications such as portfolio management, pricing, and autonomous trading, and different problems in general system optimization and control, many challenges in the Internet of Things, computing cluster optimization, logistics, delivery, and many, many others, you name it. And the important thing to remember is that RL applies to any problem that involves optimizing sequences of decisions over uncertain outcomes. So to summarize, in RL, we do not program behavior, but instead we specify goals and let behaviors emerge through autonomous learning. The current status of RL is that following exciting academic advances, RL is now taking off in industry. However, there are still lots of exciting research fronts in academia, and we're still far from completely solving RL. We don't have off-the-shelf toolboxes yet, and successful application frequently requires expertise, creativity, and innovation. In other words, what I mean is that we still need human intelligence to create superhuman RL applications. So I hope that in this talk, I convinced you that RL is a promising technology, and I can tell you that it is changing the face of AI right in these moments. Thank you.